Okay, so first of all, the main purpose of Young's double slit, or kind of the conclusion of Young's double slit, is that this proved that light is a wave. So up to this point, we've just been assuming light is a wave because I told you it was, but this was kind of thing that proved it. There was actually a controversy that thought light was more like a particle. So this proved light was a wave, not a particle. I think I'm spelling that wrong. Well, like an electron. For an electron is considered like a particle. Okay, it's a particle. It's moving, right? You can clearly see it. It has mass. Waves are different, and so this is going to be the experiment that proved it. So let me explain how this would prove it, or explain kind of the concept of what we're going to look at today. Let's say you have a gun that shoots bullets, like a machine gun, for example. Say we have a gun that shoots bullets, and if I were to shoot these bullets, let's say I shoot it towards a steel wall with two little openings. So I'm going to riddle riddle the wall with bullets. Most of the bullets will get stuck in the wall. Some bullets would pass through. If I look on the other side, what would I expect to see? There was another wall on the other side. What would I expect to see? Okay, a bunch of bullet holes. And where would the bullet holes be located? Okay, directly behind the two slits. So I'm sending all these bullets, and I know it just looks like that, but we're going to riddle it with bullets, right? So we would expect it to be a bunch of bullet holes here and a bunch of bullet holes here. Right? And they would be directly behind. What would I expect to see right behind this little blocker here? Nothing, right? No bullet holes. They should be here and here. And likewise, if light was a particle, we should expect the same thing. We should expect when we shoot light through two little openings that right here would be a bright light and right here would be a bright light. Two dots. That's what we expect is two dots, two bright lights. Okay? However, when we did the experiment, when Young did the experiment, this is what he saw. So he sent like a laser. Actually, I don't think he used a laser, but he sent a light. When we do this in class, we're going to use lasers. So he sent a light through the wave, through the holes, and the pattern that he saw on the back wall looks something like this. First of all, he saw a bright spot directly behind the barrier. So he saw a bright spot directly behind the barrier there. And then he saw another bright spot on either side of that center spot. And they were not necessarily right behind the opening. And in fact, he saw this whole pattern of spots everywhere. So instead of seeing two and only two bright spots, he saw a pattern of maybe 10 or so different bright spots, all kind of spread out and all relatively evenly spaced throughout. Alright, so this was Young's double slit experiment. This would not make sense with bullets. Okay, you would not expect to shoot bullets here and see these alternating patterns of bullet holes. Okay, definitely would not expect that for particles. So let's get into the reason why this kind of is a proof. Let's start with two properties of waves that we've maybe already talked about. One of them we have and one of them we haven't. So the first property of waves the first one is the property of interference. And we've definitely discussed this, right? Interference. This is the idea when we have, say, a wave that goes like this, and another wave that goes like this. When these two waves come together, what should happen? You should get constructive interference, what should it produce? What would the resultant wave look like? Larger wave. Okay, same frequency, same wavelength, a larger amplitude. Now with sound, this would mean you would expect a louder sound, right? What would you expect with light? Brighter light. Okay, likewise, if we had a wave that looks like this, and a wave that looks like this, yikes, those don't look good. What would you expect when these two waves come together? Destructive. So crest on trough and trough on crest, you should expect some destructive, which means, well, if they were perfect, you get a flat line, which would mean, what would you see? No light, okay, or darkness, or black. If it was perfect, it would be perfect utter blackness. So that's one property of waves that we're going to see applies to this double slit experiment. And this clearly is a wave property, not a particle property, right? You can't take two bullets, shoot two bullets and have them cancel each other out, right? If they're just going side by side, they wouldn't cancel each other out. Even if you shot them at them, even though they might destroy each other, they wouldn't disintegrate into nothing, right? There should be something there. All right, the second property of wave is what we call diffraction. These are all properties of all waves. So we dealt with this in sound, interference for sure. Diffraction we didn't really talk about, but we'll talk about it now. So diffraction is kind of the bending of waves around like edges or corners. The fact that waves bend around edges, bend around corners. So this you notice all the time with sound. So for example, if your mom's yelling at you, okay, and you don't want to hear, can you just hide in the corner down here? Because you figure, oh, sound just goes like this, so as long as I'm not here in the path of her yelling, if I go over here, maybe I won't hear. Okay, but can you still hear? Yes. And that's because as sound's a wave, as sound goes through this your open door, it actually takes kind of a path like this. It curves around, and so you can hear it basically all points. Even right now as we speak, okay, even if I face this way, so my sound is going that way, you can still hear me because it bends around, like outside my mouth it bends around so you can all hear me. I don't have to be aiming at you in order for you to hear me. So that's the concept of diffraction. And this does not happen with particles, right? If you take a bullet, you can't shoot a bullet and it's not going to bend around the door, right? As it goes through the door, it's not going to bend and turn. So that does not happen. So let's go ahead and see how this applies now to the experiment. So let's go back to it. So I'm going to send some light towards my double slit. And actually, I think I'm going to draw this bigger. Okay, so here comes our light. We're going towards our double slit. So the first idea is, if this was a particle, it would just travel in a straight line, like this and like this, right? However, we're going to say it's a wave, which means it is actually traveling, it's actually bending. So there's light going this way, there's light going this way, there's light going this way. And so each little beam, I mean, I drew 3 and 3, but you can imagine a million and a million little beams all bending throughout as it goes through the opening. Okay. Okay, so that's this diffraction property here. Okay, back here we have our little back wall where light's going to shine onto. And I'm going to take a few specific beams of light. The first beam I'm going to take is this one that comes right here and ends up directly behind. And this beam over here that also ends up directly behind. So we'll say this travels a distance L. What about this one? Does this travel farther, less, or the same as this distance L? The same, okay? Because we're taking the point directly behind the center barrier. And remember, if light was a particle, we would not expect to see light there, but we do. So here's the concept of this. Since these travel the same distance, let me do this down here, that means one's traveling, say, a distance L, and the other one's traveling a distance L. They're both traveling the same distance. So when they come together, notice you have crest on crest, trough on trough. What kind of interference should this be? Constructive. So you would expect a bright spot. Right? You would expect to find a bright spot right there. And that's what we find. So right here you get a constructive interference, which means it's bright. So rather than finding nothing, you find something, and that something is bright at that point. Okay, I'm going to draw another one. This time I'm going to use a different color. I'm going to use black. However, just understand that it's still the laser. I'm still shooting the laser. It's just to make this a little bit less confusing. So we're going to take a beam that travels here and a beam that travels here. So I'm going to say this beam on top travels a distance L again. Now this beam on the bottom, does it travel greater, less than, or equal to L? Greater. So the one on the bottom has to travel a slightly longer distance. And in fact, I'm going to choose the beam that travels exactly L plus a half of a wavelength, where that wavelength is defined by the wave that we're sending in. So if it's red, it might be like 600 or 700 nanometers, so whatever that happens to be. So let's see what happens back here. So I have my black beams traveling. So the one on top we just said was traveling L, right? So this will travel the same. So the top one still only travels L. The bottom one travels a little bit longer, a little bit farther. So I'm going to draw this one like this. Travels exactly a half a wavelength farther. So again, this is L, so from here to here it's still L. But it travels a little bit farther L. In fact, it travels exactly a half of a wavelength farther. So notice when these two waves get together, what happens? Now I have crest on trough, and so forth. So this would be destructive or dark. So in this region right here, this is going to be destructive. This is going to be a dark spot. We often call this fringe, like a dark fringe. And the path difference, we'll use that word a lot, path difference. The path difference, that's the difference between the two paths, the top and the bottom. Path difference is exactly how much? 1/2 of a wave. Okay, let's do one more. So I'm going to draw another beam. I'm going to do this in orange. However, understand that it's still the same red. So it looks like red there. So this is an orange, still the same red. So this one's going to travel distance L. The top, we'll just always make the top L. The next one is traveling farther again. Now is this the one traveling farther than L plus a half or less than L plus a half, or the same as L plus a half? Farther, even farther, right? So this one's traveling even farther. So we're going to call this L plus a full wavelength. So I'm going to draw this down here. So this one is going to be L plus a whole wavelength. So let's see what happens when it travels a full wavelength farther. So we have the first ones traveling like this, distance L. And now the next one's going to travel a whole wavelength farther. So this is still L from here to here, but we added one full wavelength. So what happens when they come together? Crest on crest, trough on trough. What kind of interference is that? Constructive. So this is going to produce constructive interference. That's going to produce a bright spot as well. Which means, if we go back to this drawing, right here would now produce another bright spot. CI, this would be bright. And what's the path difference for this? Path difference is the difference in the paths of the waves, right? This one was a half a wavelength. What's this? Full wavelength. Okay, so let's continue. You'll see some repetition here. Notice I went up, but the same thing should happen when I go down, right? So there should be a dark spot here, and there should be a bright spot here. And in fact, there's going to be more dark and bright spots. What's going to be the path difference of this second bright spot here? Any guesses? 3/2. Yeah, so this path difference is going to happen at 3/2 lambda. When's this next bright spot going to happen here? 2. So notice all the whole number wavelengths are going to produce this constructive interference. All the half wavelengths are going to produce destructive interference, and so forth and so on. And this will happen below also. And so you'll get this alternating pattern of bright, dark, bright, dark. Okay? Any questions on the concepts of this? So anyway, this shows that light's a wave because it uses two properties of waves: diffraction and interference. Without those, you couldn't explain it. Okay, you can't explain it using particles.